Hello. In the previous video, we studied inverse functions and we learned how to check if two functions are inverse of each other and how to find an inverse functions of some function. Okay. Today we study how to graph an inverse function using the graph of the original one and how to differentiate an inverse function. Okay. So let's talk about the graph using the following example. Y equal to x squared. And I consider this function only on 0, infinity. Okay, so I think we still remember the case of this function because parabola is very special case, right? Because for this parabola, the graph of this have two parts. The first part is corresponding to all values x, which are non-negative, means from here, right? I have the following graph, but at the same time, this function is an even function, so x graph is symmetric with respect to the y-axis, right? So you might have the following. You still have another branch, right? Okay, so if we consider this function on the whole number line, so the function does not have any inverse because if you pick some point y right here, right? So there are two values of x that are corresponding to y. So in this situation, the function does not have inverse. No inverse. We already talked about this in the previous video. So I will not consider on the whole number line. I restrict only on 0, infinity. Okay. That means we don't care about this. We just ignore this part. You see, we just talk about one part. Okay, so in this situation, yes, the function has inverse because the function is 1 by 1, right? And of course, we are talking about function f from where, from 0 infinity to 0 infinity, right? So I hope you still remember when we do some restriction on the parabola. Okay, all right. This is the graph of the parabola. The inverse of this is x equal to square root of y. Okay, because if you solve this equation with respect to the x, so you get the following one. Is that correct? And then you interchange x and y. F inverse of x is equal to square root of x. All right. So if you graph this function, you get the following one. You get the following one. Interesting. Here is 4, so you get something like this. Okay, this is the graph of the inverse. That is square root of x. You see? So I hope you can guess. Actually, these two graphs are symmetric with respect to the straight line y equal to x. Y equal to x. This is y equal to x. And the graph, this graph, and this graph are symmetric with respect to that. Why? Because if you have a point A and B on the graph of f of x, right? So basically, you do the inverse, right? That means the point B and A is on the graph of f to -1 of x. That is the key. So once you have A and B, so you just interchange B and A, right? For example, this is A and this is B. So you change that, right? You go to BA right here. That means BA and AB are symmetric with respect to the y equal to the x. and they happen for any points on the graph of f of x. So that's why the graph of the function f to -1 is symmetric to the graph of the function f of x with respect to y equal to x. Okay. All right. So let's graph another function and we'll see how that works, right? Just an example. Let's talk about y equal to x cubed. Okay. So let's find the inverse of this function. Inverse of this function. So if I apply cube root to both sides, I have x equal to cube root of y, and then I interchange x, y, I get f inverse of x is equal to cube root, okay, of x. So let's graph them. I will graph the function y equal to x cubed, and then I will get the graph of the function cube root of x by taking the symmetry. Okay, so I have the following: x, o, y. Let's graph this function. Of course, if we need to go all steps like in calculus 1, so we need to do that, right? Let's take the first derivative. We get 3x squared, and then one critical point, x equal to 0, and then we take y prime equal to 2 prime to check the convexity concavity. I have 6x. Again, I have one inflection point, x equal to 0, right? And if you want to see where the function convex concave, you can check this x, and then you can check y 2 prime, and then y in here 0, negative infinity, positive infinity. At 0, the second derivative is 0. When x bigger than 0, the second is positive. When x is less than 0, the second derivative is negative. So that means here you have convex, here you have concave. Okay, and of course 0 is the inflection point. Okay, concave means the function looks like this, convex is like this. Okay, and if you pay attention on the first derivative, the first derivative is always bigger than or equal to 0. The function is increasing. So I just need to pick some points in here, right? I pick 0 in here. Okay, I pick 1, -1, and 1 in here, -2. -2 would be, we have -8. Okay, -8 is very far right here. Let's try. We have this 8. Okay, so I have another point in here, 1, 2, which is very far. And then -1, I have -1, 1, I have 1. And we know when x less than 0, the function is concave. So I can draw like this. I can draw like this. Okay, so I can continue that. And in here, the function is convex. So that means, we have this part. And then, something like this. Okay, and that is the graph of the function y equal to x cubed. And we know that the graph of the inverse is symmetric with respect to the y equal to x, right? So let me draw the straight line y equal to x in here. Okay, from here I can get the graph of the function cube root of x. So I just do like this. Let me use another color. So this is symmetric, and then I go to this direction. Okay, and in here I have symmetric in here, and I go to another direction. And this is the graph of cube root of x. Okay, this is how we can draw, the graph of cube root of the inverse function. You just need to graph the original function and then make the symmetric, right, with respect to the y equal to x. Okay, now let's talk about derivative of an inverse function. Suppose that the function f is differentiable on some interval. What does it mean? That means the function f has derivative at any point on the interval I, okay? And suppose that f has an inverse function g, then the function g is also differentiable at any x for which the derivative of g is not 0. And in that situation, the derivative of the inverse can be found using the following formula. That is just the inverse of the derivative of the function f evaluated at g. Okay, so that is not this comma, right? So I just write here. Again, right, like graph of the inverse function. So you don't have to graph, even you don't need to find the inverse function. If we know exactly some function has an inverse, so you can find the graph of the inverse using the graph of the original function. You see? And in this case, yes, this formula tells you that, yes, if you know that the function is differentiable and has an inverse, you may find the derivative of that inverse using the current function. Okay, so given that you don't have to find the inverse function, that is the interesting thing. You see? So let's consider the following example. Let's say you have function f of x equal to 1/4 x cubed plus x minus 1. Okay, and the first question they ask is, what is the value of f inverse when x is equal to 3? The second question, find the derivative of the inverse, okay, when x equal to 3. All right, so let's do this. In order to find the function value, the function value of the inverse function, okay, at some point, so we need to pay attention on the following one. Okay, so if you have y equal to f of x, right, then x should be equal to f to negative 1 of y. Is that correct? That is the definition of the inverse function, because it should be 1 to 1, right? So what does it mean to find the inverse function at 3? Let's say that is x, right? So that means, f of x equal to 3. That means you have to find the x, right? Such that the function value at x is equal to 3. That's it. So I need to put, the function f of x, that is 1/4 x cubed plus x minus 1 equal to 3. And I need to solve this equation for the x. Does that make sense? And of course, you may think this equation should not have more than one solution, because our function is supposed to have the inverse, and of course this function is 1 to 1. Okay, and it has inverse. You can check that easily. If you want to check that this function is 1 to 1, I can tell you, you can take the derivative, okay, and then you have 3/4 and then x squared plus 1. The derivative is always greater than 0. The function is always increasing. Does that make sense? So if the function is always increasing, that should be 1 to 1. Okay. So let's solve this equation. Okay. So I have 1/4 x cubed plus x, and here x minus 4 equal to 0. Let's do this, x cubed plus 4x minus 16 equal to 0. Okay, so you have a cubic equation, and of course you can guess, right? I hope that you learn from high school or from pre-calculus that how to guess solution of such function. of such equation. So you might think about, you take negative 16, right, divide by 1, let's say plus minus, and then 16 by 2, and then 16 by 4, right, and so on. Is that correct? And then, you have plus minus 16 divided by 8, then plus minus 16 divided by 16. So you have a set of candidates, right? That may be a solution of this equation, and it turns out that x equal to 2 is the solution of this guy. Okay, so I will factor this polynomial by x minus 2. Okay, I have the following one: x cubed plus 4x minus 16 equal to x minus 2. Okay, you can do long division, but I can do that right away. So I have x cubed in here, I have x, that means I need x squared right here. I multiply x squared back here, I get negative 2x squared. So I need 2x squared, just to simplify with this. So I get 1x in here, that means the next term would be 2x, right? And then with the free coefficient, I get negative 16 in here, I get negative 2 in here, that means here I have 8. Okay, and this is equal to 0. From here, you can see actually we don't have another solution, right? Because this is already greater than 0. Okay, so x equal to 2. That means f of 2 is equal to 3, or f inverse at 3 is equal to 2. That's how we can solve such problem. Of course, when you read the textbook, right, they tell you, yes, you plug x equal to 2 into the equation, and you can see that, the function value is equal to 3 right away. But, we need to solve that equation. That is not just, you already have that value. Make sense? Now, let's find the derivative of the inverse function at x equal to 3. Okay, so we need to apply the formula. Yes, this one. Okay, this formula. So we need to find the derivative of the function and then apply to the inverse. You see, the inverse at that point. Okay, so let's do that. I need to find the derivative of the function. F of x derivative equal to, let me see, the function is, yes, it's this one. So derivative is 3/4 x squared plus 1. Oh, right here. Okay. 3/4 x squared plus 1. Okay. And then we know that f inverse derivative at 3 is equal to 1 over f derivative at the inverse at x equal to 3. You see, but we already know, right, from the previous question, we know, the function, the inverse function at 3 is 2. So this guy is just equal to 2, right? So this is 1 over f derivative at 2. That means you just need to plug 2 into the derivative of the original function. You see this? So I will have just 1 over 3 over 4, 2 squared plus 1. So you have 1/4, because this guy will be cancelled out. 3 with 1 is 4. And that's how we can find the derivative of the inverse function at some point. You see, this is very interesting, right? So again, right, what does mean derivative of a function? That is the slope of the tangent line at that point. So you can use that formula, the formula right here, right, to find the slope of the tangent line to the graph of the inverse function at some point, if you know the function, and if even you don't have to find the inverse. Okay, that is very interesting and very nice.